Okay, exponents and scientific notation. The scientific notation part simply extends the idea of exponents for numbers in general. But we want to know what an exponent is. If we consider 2 raised 4, two is what we call the base. And 4 is the power or the exponent. So what would that mean? So 2 raised to the power of 4 simply means I'm multiplying 2 to itself 4 times. So you have 2 multiplied to itself 4 times, which would give us 16. We don't have a problem writing 16 as 2 times 2 times 2 times 2. It's not a big deal. But what if you want to represent the number I'll take something simpler than that. Let's just say 1024, it's easier. And I want to write it in terms of 2, like I did above. And 1024 happens if you multiply 2 to itself one more, 10 times. So if you multiply 2 to itself 10 times, then you would get 1024. But that is not an efficient way to represent the number 1024, which is why if we have to express something like this, we can simply use 2 raised 10. So 2 raised 10 is an exponential number because it has a base and it has an exponent or the power. So in this case, the base is 2 and the power is 10. So if I extend this in general, is an exponential number with base a, and a obviously cannot be equal to 0. And power n. So a raised to the power of n. So that's what an exponential number is. So all we are trying to do here is find a compact version or compact way to express a particular number. So as I showed in the example earlier, I tried to write 1024 in a compact manner, which is 2 raised 10. There are some rules when it comes to exponential numbers or dealing with exponents. So no matter what base I have for any number, if I raise it to the power of 0, the answer is always 1. You could have 12,794 and you can raise it to the power of 0, it is still 1. If I have a base of 1 and I raise it to any power n, the answer would always be 1. So even if you have 1 raised negative 1, it is still 1. 1 raised negative 2 is still 1. 1 raised 1/2 is still 1. Going to put an important remark here. The base matters in the sense you can combine the bases, you can combine numbers, exponential numbers, if you have the right base. So what do I mean by that? Suppose I have a raised to the power of m and a raised to the power of n. The bases are a, and they are identical for the two terms that we have. It is a and a. So that would simply equal to the same identical base, which is a, raised to the power of m plus n. So the separate values in the exponents m and n now became an addition. So that is how we can combine two exponents if the bases are identical. This rule is called the product rule of exponents. Some people like to call it the product to sum, but product rule is good enough. In a similar manner, if we have a raised m divided by a raised n, the bases are identical. In other words, they are the same. So I can use the same base, which is a, and write it as m minus n. And that is called the quotient rule. The next rule is called the power rule. So we have a raise m, raise the entire expression to another power n. So what we do here is we write the base as is, and we multiply the powers together. So if we multiply those two, we will get m times n. Here is another case where I have a raised m divided by b raised m. Clearly, the bases are not the same. The base here is a, the base there is b. They are not the same. But if you look at the powers are the same. It's m, m. So in a scenario like this, we can write it as a over b and put it under the common power m. So in rule C, D, and E, the condition was we have the same base, or specifically in C and D, we had to have the same base. But in rule F, you have different bases, but you have the same power. So you combine the bases as A over B and put it under the common power, which is M in this case. Another rule is A over M, A raised M, which is the same as 1 over A raised negative M. Now keep in mind that there is a 1 beneath every single number. So for instance, if when we write 2, we actually mean 2 divided by 1. They are one and the same. 2 divided by 1, same. 4 divided by 1, it is the same. So there is a 1 always, but we just don't write it. So using the same argument, if we have A raised M, it means A raised M over 1. So what does the rule state here? If I move that from the numerator to the denominator, the numerator will now have 1, the denominator would have A, and you flip the signs of the power, you have negative M. So if I have A raised negative M, it is the same logic. You keep 1 in the numerator. If we move A raised negative M from the numerator to the denominator, the sign has to flip. So we would end up getting 1 over A raised positive M. So key thing to note is if you have an exponent, and if you move the exponent from the numerator to the denominator, its sign is going to flip. If you move it from the denominator to the numerator, the sign will flip. And those are the rules of exponents. So we have to write each expression here in terms of positive exponents. First thing to realize is there are 3 different bases. We have A, B, and C. So A squared, or the base A, has a positive exponent. So we have A squared divided by 1, B raised 1 divided by 1, C raised negative 5 divided by 1. So I don't have to do anything with the first exponent because it is positive. So I'll leave that as is. If I move B raised negative 1 to the denominator, I have 1 over B raised 1. And if I move C raised negative 5 to the denominator, it would become C raised positive 5. So we will have A squared divided by B multiplied by C raised 5. So here is another case where we have 7x multiplied by y raised negative 4. There are 2 bases, x and y. 7 is also a base, it's raised to the power 1. once you're familiar with the process, you don't have to write out the way I'm doing it. So 7 over 1, x over 1, y raised negative 4 over 1. The first two terms have positive exponents, so we'll simply have 7x. When that moves to the denominator, we have 1 over y raised 4, which would give us 7x over y raised 4. Okay, the first thing to notice here is we have two bases. One is x, and the other, you call it z. I'm used to calling it z, but it's the same thing. So x raised negative 7 over 1 multiplied by 1 over z raised negative 3. So if we multiply those two, I will get z raised negative 3. If I multiply those two, I would get x raised negative 7. Again, you don't have to do it the way I'm doing it. I'm doing this for instructional purposes, but once you have enough practice, you'd be able to do this without writing all this stuff. So if x raised negative 7 moves from the numerator to the denominator, we will have 1 over x raised 7. If z raised minus 3 moves from the denominator to the numerator, we will have z raised negative 3. Oops, positive 3. Divided by 1, which is the same as z raised 3 over x raised 7. Okay, so we want to simplify using multiplication rule, and the key thing here is to look at the bases. The bases in this case are identical. Base 3, base 3. So if the bases are identical, we simply write that common base and add the powers. The powers here are 3 and 5. So 3 raised 3 plus 5, which would give us 3 raised 8. In that case, again, the next problem, we have the same base, and the base here is n. So if we write n, it means n raised to the power of 1. So we just don't write that 1 each and every time. Anytime we have n, it's n raised to the power of 1. If you have 2, it is 2 raised to the power of 1. So it is a given. So we have an identical base, which is n. So we look at the powers, 1, 10, 12. We just add those powers, 1 plus 10 plus 12. We get n raised to the power of 23. So we want to use multiplication rule in this case. And in a problem like this, I recommend students to group the terms or rewrite it by grouping the terms, because you're simply multiplying a bunch of exponents. What do I mean by grouping? So I'm going to combine all the numbers together first. So I have negative 6 and I have negative 3. And write all the a terms together. So I have a squared multiplied by a. So I have a squared, a, wrote them there. I'm multiplying, so the order can be different. So b cubed, just right here, multiplied by another b cubed. So -6 times -3 is positive 18. The bases are identical for the a's, so we add the powers, 2 plus 1. The bases are identical for the b's, and 3 plus 3. We add the powers, so we would end up getting 18 a raised 3 times b raised 6. So here we have to simplify using quotient rule. The base is simply x, and it is identical. So if we use the quotient rule, we can put that identical base and raise it to the power of 9 minus 4. The numerator power minus the denominator power. So the answer is x raised 5. The grouping that I mentioned with product rule is more so important when it comes to quotient rule, because you wouldn't make mistakes if you grouped terms. What do I mean by that? So I'm going to group all the a terms first, that is the first base, a raised 12 over a raised 9 multiplied by b raised 2 over b. The bases are identical for the first term, which is a, numerator power 12 minus the denominator power 9. The bases are identical between the numerator and the denominator in the second fraction. Numerator power minus the denominator power. So a raised 12 minus 3, or 12 minus 9 is 3. B raised 2 minus 1 is just 1. And we don't have to write that 1 each and every time. It is simply a cubed multiplied by b. Okay, I'm going to group the terms. So 24 and 10 are numbers, so I'm going to write it that way. I'm able to do it because the terms are in product. You can't do this if you see pluses or minuses. So multiplied by a raised 10 over a, multiplied by b raised 11 over b raised 3. A 2 is in common between 24 and 10, so 12 times and 5 times. 12 times 2 is 24, 5 times 2 is 10. So we have 12 over 5. Have a common base of a, 10, minus 1. The denominator power is 1. Common base of b, 11, minus 3. So 12 over 5, a raised 9, b raised 8. And that's the final answer.